So, the theorem is as follows. So, the theorem is theorem number 6, or the theorem of the Lagrange multiplier rule. Lagrange multiplier rule. So, let omega, a subset of Rn, be a region, subset of Rn be a region, and let f from omega to R, or g from omega to R be smooth functions, and if I have that f has a local extrema, f has a local extrema at x bar in omega, the local extrema, the vector, we are talking about Lagrange multiplier in multiple dimensions. So, before that I must have said that Lagrange multiplier method is certainly valid for higher dimensions. So, can be extended to higher dimensions. Okay. So, we are talking about the case in n dimensions here. So, suppose the local extrema is x bar, subject to the constraint g of x is equal to 0, and such that the gradient of g at x bar does not vanish. Then there exists a lambda such that the gradient of f minus lambda g is equal to 0, right, and this rule is true for Rn, where n is any integer. Okay. So, then how about the scenario when we have multiple constraint, more than one constraint? It turns out that Lagrange multiplier works there as well. So, let me highlight with an example. So, in the case of multiple constraints, we are going to extremize f from omega, which is a subset of Rn, to R, omega which is a subset of Rn to R, subject to m, which is typically less than n, or the dimension of the space, m constraints. Okay. So, then I have that gk of x bar. So, I have constraints like of the form gk of x bar equal to 0, where k is from 1 to m. There are m constraints, right. So, the necessary condition in this case, the necessary condition given by Lagrange reduces to the following. It tells us that grad of f of x is equal to the summation of the lambdas times grad of g of x, where k is from 1 to m, right. So, let me call this condition as star, and further we need to generalize the condition. We need to generalize the condition that the grad of g is non-zero as follows. To look at the fact, now we are talking about problem having multiple constraints, and it could be a problem in Rn, right. So, let us say the general situation is where x is a vector, right. So, we have multiple constraint in multiple dimensions. So, to generalize this condition that grad g is not 0, let us consider the following matrix, right. So, consider this matrix M of x bar, which is grad g 1 of x bar, grad g 2 and grad g n, so on and so forth, right. So, this is M. Okay. So, expanding further, this is nothing but the matrix del g del x 1 and so on, del g del x n del, well, this is g 1 del g m del x 1 to del g m del x n, right. So, now we have an M by n matrix, M by n matrix, now also known as the augmented, well, also known as the Jacobian matrix, the Jacobian matrix, right. So, students who have done a bit of multivariate calculus can immediately tell me that generalizing the condition grad g not 0 would lead to the fact that the Jacobian will be such that the determinant is non-zero, right. Not only that, we need something more, right. So, first of all, let us say, so let us say now, so to generalize the condition that grad g is not 0, this is equivalent to saying, so the generalized version, right. In this particular case of multiple constraint, it is equivalent to saying that the rank of M of x must be at least 1, right, which means at least one component of grad g is non-zero, right. So, there is at least one non-zero row of this Jacobian matrix. Okay. So, then further since I have that grad f is summation lambda k grad g, so that is via the Lagrange multiplier method. It also tells me that grad f is linearly dependent on the family grad g k, right, k from 1 to m, right. It is linearly dependent on this set of vectors, which means that look at this augmented matrix. So, the augmented matrix look at this augmented matrix, I denote it by M f of x bar, which is also equal to all the top rows are given by the Jacobian matrix, the last row is given by grad f. Now, what can we say for this augmented matrix is that since the last row is linearly dependent on all the above rows, which means that the rank here of MF will be bounded above by the rank of M, right. The rank of MF is bounded above by the rank of M, because the last row is linearly dependent. Okay. So, we are ready to state the result for Lagrange multiplier with multiple constraint. So, let me state it in the form of a theorem number 7. So, let omega be a subset of Rn and f is a function from omega to Rn, omega to R, and I have the constraints gk. Gk's are set of functions from omega to R, be smooth functions for k equal to 1 to m, and if f has a local extrema, at x bar which belongs to omega, subject to the m constraints, which are given by gk equal to 0 then what I have is, so let me call this as double star, right, and the condition double star is satisfied, the condition double star is satisfied, then what I am going to get is, let us say it is satisfied at x bar, then there exists a lambda I such that grad of f minus summation, there are lambda i's such that grad of f minus summation lambda i's grad of g i's is equal to 0, right. So, that is what we have, seen so far, and that has now been compiled in the form of a theorem. Okay, so, let us look at this situation of multiple constraint with an example. Okay. So, find the local extrema, of f of x bar, which is x 3 square by 2 minus x 1 x 2, subject to g of, well, we have two constraints. So, g 1 of x is x square, x 1 square plus x 2 minus 1 equal to 0, and my second constraint is g 2 of x bar is x 1 plus x 3 minus 1 is equal to 0. So, find the local extrema of this subject to these two conditions. Now, so how are we going to approach this equation? We will just use our Lagrange multiplier constraints to begin with. So, I have defined my Lagrange multiplier constraint as star. Here is the condition, right. So, let me call this as star. So, from star I see that I can directly find. So, here I have that n, the total number of variables are 3. So, n is 3 and the number of conditions m is 2. So, the equations that I get from the Lagrange multiplier methods will be 3 in total from the gradient condition, and we have two constraints. So, so I am directly writing my conditions coming out from star. So, these are my three relations which can be checked very easily, right. So, I get the second one is x 1 plus lambda 1, this is equal to 0, and the third one is x 3 minus lambda 2, which is equal to 0, and students can see that there are three variables x 1, x 2, x 3, and two constants also unknown lambda 1 and lambda 2. So, these are my three equations, and subject to the condition g 1 is equal to g 2 is equal to 0, I will immediately be able to solve this system. It gives me 2 points. The first point, I am directly writing the answer. The students are asked to check that this is indeed the solution, right. The first point is this quantity, and the second point is this quantity 2 by 3, 5 by 9, 1 by 3. So, these are my solutions, right. Okay. So, then given I get my lambda 1 to be negative 2 by 3 and lambda 2 to be 1 by 3, right. So, for omega, so let us now check about the uniqueness of the solution that we have got, or so let us see what happens to the rank of the Jacobian matrix and the augmented matrix for these two solutions. Now, for omega, if we calculate the Jacobian matrix M of omega, we see that it comes out to be the following: 2 cross 3 matrix, minus 2, 1, 0, 1, 0, 1. It is easy to check because all I have to do is to find the necessary derivatives of this conditions of this constraints, right. So, this is nothing but del g 1 del x 1, del g 1 del x 2, del g 1 del x 3, del g 1 del g 2 del x 1, del g 2 del x 3 del x 2 and del g 2 del x 3, right, evaluated at -1, evaluated at the point w, right. Now, similarly, if we check the augmented matrix, the augmented matrix is comes out to be -2 1 0, the first two rows are the same and the last row is 0 1 2. Notice that in this case row 3 is nothing but row 1 plus 2 times row 2, right. So, the last row is linearly dependent as expected, or the rank of the augmented matrix is less than, or in this case exactly equal to the rank of the Jacobian matrix. Okay. So, what I get is, so this condition is certainly true, which guarantees that grad g is non-zero, right. So, through this we are guaranteeing that we are not dealing with pathetic cases. Similarly, we can check. So, similarly check, the students are asked to check that this rank, so let me call this as my condition A. So, A holds for the other solution that we had z bar, right. Okay. So, which means that w and z both are extremas or local extremas that are found using Lagrange multiplier. So, it seems that Lagrange multiplier is the way to go. It presents a very rosy picture and allows us to solve almost all different class of problems. But now next I am going to show another class of problems where the Lagrange multiplier creates some problems or completely fails. So, those class of problems are going to be denoted by abnormal problems. Abnormal problems. Now, what are these class of problems? Of course, we have seen that throughout our lecture discourse, we have assumed this following constraint, right. This is what we have assumed so far, right. How about when this is not true, that is grad g, the constraint, the gradient of the constraint is 0, and then we will see that we run into some troubles. Okay. So, the Lagrange, it turns out that the Lagrange method breaks down when grad g is 0, right, and we will see how. Or this is equivalent to saying that the rank of the augmented matrix not necessarily less than equal to the rank of the full matrix or the Jacobian matrix, right. So, when this inequality is not satisfied, we will run into trouble, right. So, which means we have two class of problems. So, the first class of problem is that we have this Lagrange setup, this is equal to 0 and we have that grad g is non-zero. So, those are the class of problems very easily solved by Lagrange multiplier. We call them as normal problems, right. And we could have another class of problems where again the Lagrange setup gives some equations, but grad g vanishes, right, and those are the class of problems we call as abnormal problems. That is, the points that we find from Lagrange setup does not satisfy the gradient criteria. Okay. Now, it turns out that, so what is so difficult, or what is the difficulty about gradient vanishing? It turns out that gradient vanishing, even if gradient vanishes, gradient of the constraint vanishes, we may still be able to find the solution, but we run into trouble like the derivative of the derivative vanishes or the derivative does not exist of the objective function and similar such problems, right. So, grad g 0 may lead to problems of the sort that the solution set to G equal to 0, 0 need not form smooth curves. Solution to 0 need not form smooth curves, and the second is that the curves may have corners or cusps. The curves may have corners or cusps, right. So, the solution set G equal to 0 need not form smooth curves, and the curves may have corners or cusps, and our next set of few examples are going to exactly show these difficulties. Okay. So, let me show this class of problems, the problems that we face via some examples here. So, here is one quick example. So, I have my objective function f is x square plus y square, and my constraint function g is y minus 1 whole cube minus x square, right. Extremize, the problem is extremize f subject to g, extremize f subject to g. When we do that, again we start solving by setting up the Lagrange constraint. We take the gradient of f minus lambda g equal to 0, and we are going to get set of two equations. The first equation is x 1 plus lambda equal to 0, and the second equation is 2y minus 3 lambda y minus 1 square is equal to 0, right. Now, we have three unknowns x, y and lambda, and of course, we have the constraint g. It seems everything is nice, but notice the first equation. So, let me call this as 1 and this as 2. So, from 1, if I set x equal to 0 and I use g equal to 0, I get y equal to 1 as my solution. However, from 2, which is independent of x, when I plug y equal to 1, we have no solution, right. Y equal to 1 does not, y equal to 1 does not does not provide us any solution, right. And further now, which means that we should perhaps explore the other condition, lambda equal to minus 1. So, if I take lambda equal to minus 1, right, then from condition 2, I get the following equation: 3y square minus 4y plus 3 is equal to 0. It turns out that there is no real solution to this problem, right. So, we are stuck. It seems that there is no extrema, and the Lagrange method completely breaks down. Now, but something still can be done. Notice the following. Notice that the only solution that we found, although it did not satisfy the constraint, the only solution, perhaps the only solution that we found was 0 1. Perhaps I should definitely write the word perhaps, because we have shown that it doesn't, there is some problem here, right. So, perhaps the only solution, the only promise that we were getting was at point 0 1, right. So, notice that at this point, if we were to evaluate the grad of g, right, we will see that when we plug y equal to 1 and x equal to 0, I am going to get grad of, of course, we take the gradient, we will still get at this point this is equal to 0. So, the gradient of g vanishes. So, this is certainly an abnormal problem. So, the idea here is that the abnormal problem cannot be approached via the Lagrange multiplier method. Now, geometrically, let us see what is the problem happening. What is so problematic about this example? Now, if we were to look at the level curves of f, let us say the level curves of f, which will be f equal to a constant. I know that these are circles, right. So, x square plus y square is equal to c are circles which are having its center at the origin, right. And if I were to plot, so this is my level curves f is equal to c, and if I plot my g equal to 0, we will see that it looks as if it is the following, right. So, at x equal to 0, so this point is 0 comma 1. So, at x equal to 0, we see that it forms a cusp point, right. So, the derivative vanishes, as has been readily shown here, right. So, which means that this sort of a method where we are taking the derivative of the net of the function will not hold, because the derivative vanishes for the condition, for the constraint, right. So, that is why the Lagrange multiplier fails, because we are assuming that the derivative is available for us, right. Well, it is not vanishes, but the derivative does not exist, right. So, we will have a problem at this point. Okay, so then let us look at another example. Now, I am going to take my objective function f to be x square plus y square, and I take my function g, the constraint, to be x square minus y square, right. So, in this case we see that if I set up my Lagrange condition f minus lambda g equal to 0, I am going to again get a set of two equations. Let me quickly write them down. X minus lambda is 0, and the other equation is y 1 plus lambda is equal to 0, and we see that, let me call this as A and by B, and we see that certainly x equal to 0, y equal to 0 satisfies the condition. So, if I choose x equal to 0, then I get the solution y equal to 0 from g, the condition g equal to 0, right. And if I choose lambda equal to 1, or x not equal to 0, then I still get y is equal to 0, but y equal to 0 gives me x equal to 0, right. So, this is not possible. This setup is not possible, which means that the only solution that we get is 0 0, and lambda is arbitrary, right. Any value of lambda will satisfy for this point 0 0. Now, it turns out that further, notice the objective function. The objective function is a real valued function with square of its variable, and it is easy to see that the minimum of the function will be obtained at x equal to 0 and y equal to 0. So, the point that we got is minimizing the objective function, right. So, what is happening here? So, it turns out that 0 0 is the global minima of f, because f is greater than equal to 0 and f is equal to 0 at 0 0, right. So, it is a global minima, and let us do the same exercise, try to draw f and g. So, g is the constraint, which is this. So, if I were to draw this level curves, notice the level curves of f are again this following function. So, if I were to draw these level curves, we see that the level curves are as follows, and if I were to solve this constraint g, I see that the constraint is y is equal to plus minus x, right. So, these are pairs of two straight lines which are passing through the origin, which means that the only level curve that satisfies g will be the point at the origin, right. Okay. So, what I have is, so what I have just now showed is the following. So, f 0 0 is the global minimum of f, and this critical point 0 0, this critical point 0 0 will be the same for any constraint which passes through 0 0, will be the same for any constraint g equal to 0 which passes through the origin, right. So, as I do not care about what the constraint is here, in fact, constraint plays almost minimal role. As long as the constraint passes through the origin, it is quite clear that the critical point 0 0 0 0 will be an extremal to this constraint optimization. So, in this case, the constraint is playing a passive role, or this is a case of a passive constraint problem. Okay. So, the constraint plays a lower role than the objective function.